Hello everyone, welcome to CSEN 503, Introduction to Communication Networks. This is Dr. Amr Al-Mugi. Last lecture we were discussing the transport layer. We started by giving an overview of the transport layer, and then we discussed the header of UDP, and then we focused our attention to TCP. We saw a brief overview of its header, which looks like that. And we discussed the first service in TCP, which is reliable transport. We saw how TCP specifies sequence numbers and acknowledgement numbers. And we saw examples of how TCP deals with packet loss events. And the last thing we discussed last time was the fast retransmit protocol within TCP that allows TCP to actually recover from a packet loss faster than actually waiting for a timeout, which is when the sender receives 3 duplicate acknowledgements for a packet, it retransmits the packet directly without actually waiting for the packet to time out. But today we are going to discuss the remaining services of TCP. In particular, we will discuss flow control, congestion control, and connection management. We will discuss first actually flow control. Flow control is a service that is offered by TCP such that a fast sender does not overwhelm a slow receiver. We have in TCP 2 endpoints of a connection. We have a client and we have a server at the other end. One of them may be faster than the others, meaning that what we have here, we have the layers of the protocol stack within a device. At the top, we have the application and we have the transport. Same thing is available at the receiving end. And of course, all the layers below it. We know that the job of the transport layer is to process the data and give it actually to the application layer free of errors and in sequence. What will happen if there is a fast sender that is actually sending at a very fast rate to the receiver? The problem is, in order for the transport layer at the receiver to give the data to the application layer, this involves a little bit of time. It involves a little bit of a processing speed, meaning that the application layer needs actually to read the data from the buffers at the transport layer. This is what happens when you establish a TCP connection. Both sides actually establish or reserve some buffer space for this connection, and any incoming data is put in this buffer space waiting for the application to read it. If the data arrives in sequence and without errors, it will be put actually in the receive buffer, waiting for the application layer to read it. And the application layer, of course, will not read this instantaneously. It will read it at a certain speed, which is the processing speed, and it might be slower than the rate at which data is arriving. So if you have a very fast sender, it may be filling the buffers at the receiver at a very fast rate, and the application layer would not be able to read this data in time, leading actually to the buffer being full and eventually overflowing. Flow control is the service that prevents this from happening. It prevents a fast sender from overwhelming a slow receiver. And just like reliable transport, flow control also depends on feedback directly from the receiver to the sender. Okay, this feedback is called the receive window. Basically, every device, the 2 endpoints of the connection, will maintain something called the receive buffer, which is the total buffer space that is available for this TCP connection. At any given time, this buffer space, part of it will be full, meaning that part of it will actually have data waiting for the application layer to read it, and part of it will be empty. This empty buffer space is waiting for more data to arrive from the sender, is available for the sender to actually send to it data. We call this unused buffer space the receive window. And so at any given time, the sender will restrict the amount of data that is sent to the receive window. If we take a look back at the TCP header, we will see that there is a field here in the TCP header called receive window. That means there is an explicit notification within every packet of the remaining buffer space at the receiver. The sender will actually receive the packet, including the header, which includes the receive window, and will restrict the amount of data that is sent to this receive window. With time, the application layer at the receiver will process some of the data and so will empty up some of the buffer space that is already full, meaning that the receive window will increase. And so in the next packet that is sent by the receiver, it could be even an acknowledgement packet, anything that has a TCP header, the new receive window will reflect that there is more available buffer space at the receiver. And so the receive window can actually be seen as a sliding window. It shrinks and it expands depending on how much unused buffer space is available at the receiver. And so we can see some examples just to see how this is happening. Imagine that you have a client and the server, as you see in this figure, and they have established the TCP connection. Okay. And in the TCP connection, they told each other about the available buffer space that each of them have. Let's say the server told actually the client that it is reserving a buffer of size 360 bytes. So the client will now know that the sending window is 360 bytes. That's actually the buffer space. And out of this 360 bytes, none of them are used, meaning that all of the buffer space is empty. And so it indicates that the usable part is 360 bytes. And so it sends the first packet. Let's say the first packet has length 140 bytes. Of course, it has sequence number 1. This packet arrives at the server. Once it arrives at the server, it consumes 140 bytes from the receive buffer, meaning that the receive buffer, once the packet arrives, is 360 minus 140, which is equal to 220. However, at the same time, the application layer is reading some of this data. Okay, so this is 220. The application is reading some of this data. Let's say at this point, the application reads 40 bytes, meaning that by the end of this process, the available buffer space that the server will send back to the sender is 360 minus 100, which is 260. Okay. Why minus 100? It was initially 360. It received 140. So the available buffer space is actually 220. And it read an additional 40 bytes, meaning that it emptied an additional 40 bytes on top of the 220. So 220 plus 40 bytes gives you 260. Okay, so it sends back to the sender that right now the available buffer space is actually 260. And you can see here the acknowledgement number is 141, indicating the next byte that the server is expecting to receive from the client. Once the client receives this information, it will now update its sending window size to 260, and the available part of it is 260 bytes. Okay? And so the next packet that is sent, let's say it sends another 180 bytes, and this one will have sequence number 181. Let's say this is received and the server actually responds right away, meaning that 180 bytes will be consumed from the buffer. So that's 260 minus 180, giving me 80 bytes available. So now the server will respond back to the client saying that there are only 80 bytes available in the receive window. The client will update the receive window with this information, indicating that the receive buffer is now 80 bytes. Okay. The next packet that is sent can be maximum 80 bytes. The sender cannot actually send any more data than that. Once actually the sender sends the 80 bytes, it has to stop. It cannot send any more until it receives an updated window from the server. Okay. Once the 80 bytes are received, these occupy completely the buffer at the server, and now the receive window is empty, and it sends back window equals 0, means that the sender cannot send any more packets. It has to stop until the application actually processes some of the data in the receive buffer to empty an additional buffer space, and then the server can send an updated receive window to the client, indicating that it can resume sending packets. Okay, so if we take, for example, this step here, the usable space was 220, and the sender sent a packet of only size 180 bytes. The sender does not have to wait for the receiver if there is still usable buffer space. That means the sender can send any number of bytes. If the usable buffer space is 220, it can send any number of bytes up to 220. It can send them all in one packet, or it can send them over several packets. Whatever it is, the sender is allowed to consume the usable buffer space without waiting for feedback from the server. Once the usable buffer space is consumed, it has to wait for the server to tell it that there is actually an updated receive window that is now available. Okay. Okay. Another example, let's say the window start at capacity 360, and the first packet that is sent by the client has actually size 360, and so it consumes the receive window completely. So initially it is 360 minus 360, but let's say the application was able to read some of this data, and so the window was reduced only to 120. And so this is sent back to the client, indicating that the receive window is now 120. Okay, and so the client restricts its sending rate to only 120. And so this is sent. Let's say the window now is reduced to 80, meaning that 120 are received, but the server processed actually out of them 40 bytes yes, to 80 bytes, and so the receive window is now reduced to 80. Okay. Okay, and it goes on. Every time the sender restricts or updates its receive window according to the feedback it is receiving from the server, and accordingly sends the next packet restricting itself to this size. This is the flow control process. It is a straightforward process, and it depends on direct feedback from the server to the client, explicit feedback, meaning that the information about how many bytes can be sent from the sender are explicitly mentioned. The client does not have to infer them. The client doesn't have to estimate them. They are actually explicitly mentioned to the client by the server. And since TCP is a bidirectional communication protocol, that means either side will have a receive buffer. They don't have to be of equal size, obviously. Each side of the TCP connection may indicate its own size of the receive buffer in the TCP connection establishment phase, and they will update each other with the value of the receive window in every TCP header that is sent. And we know that every packet will actually carry a TCP header, and so every packet will carry a new update of the receive window. This is the flow control process. Next, we will discuss the TCP congestion control process, which is a little bit different. The common thing between congestion control and flow control is that both of them aim to adjust the sending rate of the sender. That means both of them will tell the sender how much data they can send at this time. Okay. However, the goal of the congestion control protocol is not to overwhelm the routers between sender and the receiver. We know that at any given time, we have actually routers between sender and the receiver, and these routers also have a limited buffer space, and if this buffer is full because the router is receiving too many packets, it will start to lose packets. Now, it is not in the interest of the sender, if this is the client and this is the server, it is not in the best interest of the client and the server for the router to lose packets. Because if the router loses packets, then the packets will not actually arrive, and eventually the packet will time out and will need to be retransmitted, which will cause a lot of delay. So it's not in the best interest of the client or the server for the routers to lose packets. And so congestion control is a service that adjusts the sending rate of the client and the server such that it does not overwhelm the routers. Meaning that if the client or the server indicate that there is actually a problem in the router, that means the router is actually overwhelmed with packets, and so it will not make sense for the client or the server to send at a very fast rate. They will restrict the rate such that to reduce the load on the routers. Okay? If they indicate that there is no problem, that all the packets are actually being delivered, then they will actually increase the rate because they will think that there is no problem actually at the router. Now, the question here is, how does the client and the server know what is happening at the router? When we discussed flow control, we said that flow control actually depends on explicit feedback from the server to the client or from the client to the server, which is the received window. This is an explicit piece of information that is actually included in the header. There is no such thing coming from the routers, meaning that the routers will not actually tell the client and the server how much buffer space is available to them. And we know why. We know that the routers actually operate only at the network layer, so they have network data link and physical layers. They don't have a transport layer, and so they don't run TCP. There is no TCP connection between the client and the router, or the server and the router. There is only a TCP connection between the client and the server. And so there is no means by which the router can provide the TCP layer at the client and the server with its updated buffer space. And so the client and the server must actually estimate what is happening at the routers between them and accordingly adjust the rate. Okay, it's not just actually an estimation. It's actually an estimation of the overall connection between the client and the server. Meaning that if there is a problem at one of the routers between the client and the client and the server will have actually no way to learn which router is actually having a problem, nor do they care. All the client and the server will care about is whether the connection between them is actually good, it is capable of accepting high rates, or is it poor and I have to actually reduce the sending rate. This is all they care about. And so the client and the server will actually use the quality of the connection to estimate the load over the routers. Meaning that if they see that the connection between them is able to deliver a number of packets, then they will think that the connection is fine and they can increase the rate. Once something happens in the connection, they indicate that indicates that the connection is poor, they will start actually decreasing the rate. Now the question is, what can they use to indicate that the connection is good or bad? They already have a mechanism of feedback between them, which is the acknowledgements and the timeout events. Okay? If the client actually sends data and gets feedback from the server that they have arrived, meaning that it receives acknowledgements, then this is an indication that the routers are actually delivering the packets to the other side, meaning that the connection is a good one because the packets end up actually going to the other side. If the packets take too long to be delivered to the server or to the other side, that a timeout will occur, then this is an indication that the queuing delay is too high, or even that a packet loss event has happened at the route. And so a retransmission will happen, obviously, from the client or the server, wherever actually the timeout occurs. But not only that, the client or the server will reduce their sending rate. They will reduce the rate of pipelining, the number of packets that are sent per round trip time. Okay, so that it's an indication that the connection is now actually not performing very well, and so it doesn't make sense to keep the sending rate very high, and so they will have to actually reduce the sending rate. Now at this point we have the overview of congestion control, and we have also flow control. Each of them will maintain a window. The congestion window is called CWND. This is the sending rate that is dictated by the congestion control protocol, and we already have the receiving window or RWND, which is determined by the flow control protocol. So we have two windows that the sender has to maintain. Okay? Now the question is, which rate will the sender follow? Which rate will actually constrain the sending rate of the sender? The answer is the minimum of the two. If congestion window is smaller than the receive window, then the problem is actually in the congestion part, and so the sender will restrict its sending rate to the congestion window size. If receive window is the smaller one, that means the problem is actually in the flow control, and so the sender will restrict its sending rate to the size of the receive window in this case. Both protocols operate independently. Flow control operates based on explicit feedback from the receiving device. Congestion control is maintained by an estimation. It's not maintained by any explicit feedback. It's just maintained based on actually observing how many acknowledgements are received within a round trip time and how many timeout events actually occur. Let us now take a look at how exactly do devices, or how exactly does TCP do this estimation task. How does it estimate that the connection is good, whether actually to increase the sending rate or decrease the sending rate? This is done based on something called a congestion avoidance mechanism. Okay? And there has been many of them across the years, ever since TCP was first proposed. I think it was the early 70s or something like that. Ever since it was proposed, there has been several versions of the congestion avoidance protocol that operates within TCP. The earliest one was called TCP Tahoe, and there has been other ones such as TCP Reno, Vegas, Cubic. We will see some of them in this lecture. So let us actually start with TCP Tahoe, see how it works. Okay. The idea is with TCP Tahoe is that you have actually host A and host B, and obviously there should be several routers between them. And they don't know what the routers have. They don't know whether the routers are overloaded or not. So TCP Tahoe will actually start conservatively, meaning that it will start by probing the network between A and B. It will start with the minimum sending rate, which is equal to 1 MSS per RTT. MSS is actually short for maximum segment size. It's the maximum size of a segment that TCP can make. We said last time that TCP receives actually a stream of bytes from the application layer and creates segments out of these bytes. It takes a chunk of bytes and creates a segment. There is a maximum number of bytes that TCP is actually allowed to take from the application layer, and it is usually determined by the type of physical connection that the host has. Regardless of that, there is actually a maximum segment size. Okay, so in TCP Tahoe, host A will start conservatively. It will start with the minimum sending rate, which is 1 MSS per RTT, meaning that in the first round trip time, host A will send only one segment, as you see in this figure. Okay, meaning that the congestion window size is 1 MSS. Okay. There is also a threshold that is set initially, and it is typically set to 64 kilobytes. Sometimes it's just set to the maximum capacity of the communication channel. We will get back to SS threshold later. So in the first round trip time, host A sends one segment. Now, one of two things will happen. Either this segment will actually make it all the way to host B, in which case host B will reply with an acknowledgement, or the segment will be lost, in which case a timeout event will occur at host A. In this case, as you see in this figure, the segment actually makes it to host B. That means the routers between host A and host B will deliver the segment, and host B will reply with an acknowledgement. If the acknowledgement goes back to A, then this is an indication that the segment has been delivered to B. And so in this case, what the TCP Tahoe protocol will do is that it will increase the size of the congestion window exponentially, meaning that for every acknowledgement that is received, it will increase the size of the congestion window by 1. And so in the first round trip time, it received 1 acknowledgement. And so it will increase the size of the congestion window by 1, meaning that the congestion window now is equal to 2. So in the first round trip time, congestion window was equal to 1. Here, congestion window is equal to 2, meaning that it is going to send 2 segments in the next round trip time. Okay. Now, in the second round trip time, 2 segments are sent. This is actually the pipelining feature. We know that in TCP, you can actually do pipeline. Either the segments will be delivered or they won't. If they are delivered, then 2 acknowledgements will be sent back to A, or it can be 1 cumulative acknowledgement. It doesn't matter as long as host A learns that 2 segments have actually been delivered at B. And in this case, the TCP Tahoe will actually increase the size of the congestion window by 1 for each acknowledgement. So it receives 2 acknowledgements. It increases the congestion window size by 2, so it becomes 2 plus 2, which is equal to 4. So it sends 4 segments. If it receives 4 acknowledgements, it will increase the congestion window to 8. If it receives 8 acknowledgements, it will increase it to 16 and 32 and so on. So the congestion window will increase exponentially in size. The question now is, until when? There are actually several things that can happen. The first thing is that the congestion window reaches the full capacity of the channel, the full capacity of the connection at host A, meaning that host A cannot actually send at a higher speed. And this is the desirable outcome. This is actually what TCP Tahoe, all congestion avoidance mechanisms try to do, which is to make the sender actually reach the maximum size of the window without there being packet loss events. If it does that, then it would have achieved its objective fully. So this is one case that you keep increasing the congestion window until you actually hit the full capacity of the channel. Another case would be is that you increase the congestion window by a value that is large enough that it starts to overwhelm one of the routers, in which case an event would happen. And the event here is that either a timeout will occur, meaning that one of the segments that you send will not actually be delivered, and so you will not receive an acknowledgement for it, and eventually a timeout will occur. Or the other event is receiving 3 duplicate acknowledgements. From the fast retransmit discussion, if you remember here, receiving 3 duplicate acknowledgements was an indication that the packet was lost, because you keep receiving acknowledgements for the first one, and it's an indication that the packet in the middle was actually lost. Okay, so a timeout may happen, or the sender may receive 3 duplicate acknowledgements, or in another case, the congestion window size may increase to be equal to or greater than the value of SS threshold, which we initiated to 64 kilobytes. We said that it can also be initiated to the maximum size of the channel. If congestion window hits SS threshold, we will go to what is called congestion avoidance state. And in congestion avoidance state, we increase the sending rate, but in a more conservative way. In this phase, which we call the slow start phase, we were increasing the size of the congestion window exponentially. That means in every round trip time, if you receive acknowledgements for all the packets, you double the size of the congestion window, meaning that you increase the congestion window by 1 for every acknowledgement that you receive. In congestion avoidance, you will increase the congestion window by 1 for every round trip time. That means in the second round trip time, if you send 2 segments and you receive 2 acknowledgements, you will only increase the congestion window to 3. If you send 3 packets and you receive 3 acknowledgements, you will increase the congestion window to 4. If you send 4 and receive 4 acknowledgements, you will increase it to 5, and so on. Okay? So in the congestion avoidance phase, you actually increase the size of the congestion window linearly and not exponentially. In the case of the other 2 events, either a timeout occurs or 3 duplicate acknowledgements, this is an indication that the packet is lost. And TCP Tahoe does not differentiate between how a timeout event is treated or how a 3 duplicate acknowledgement event is treated. In both cases, what will happen is the congestion window will be reduced to 1 MSS, that means it will be reset, and SS threshold will be reduced to whatever size of the current congestion window divided by 2. Okay? So congestion window is equal to 1 MSS, SS threshold is equal to congestion window over 2. And then it enters slow start again, meaning that congestion window is equal to 1, sends a segment, receives an acknowledgement, increases congestion window to 2, sends 2 segments, receives 2 acknowledgements, sends 4, receives 4 acknowledgements, sends 8, receives 8 acknowledgements, and so on. It will keep doing that until either another timeout or 3 duplicate acknowledgement events occur, in which case the same thing will happen. Congestion window will be reset to 1, SS threshold will be decreased to congestion window over 2. Or congestion window will hit SS threshold, in which case the sender will go into the congestion avoidance phase. So at any given time, if you start from scratch, you go to slow start. Here, you increase the congestion window size exponentially until either a timeout occurs or 3 duplicate acknowledgements, in which case you reset the congestion window to 1, and SS threshold is equal to congestion window over 2, and you increase exponentially. Once you hit SS threshold, in any time you hit SS threshold, you will exit the slow start phase and go into the congestion avoidance phase. And there you increase the size of the congestion window linearly for every round trip time. So you increase by 1 for every round trip time. Okay. This is TCP Tahoe, and this is actually an example of the numbers. So we start in the first round trip time. Here, initial congestion window is 1 MSS. Let's say 1 MSS is equal to 1 kilobyte, and as the threshold is 64K. And so if nothing happens, congestion window will be increased to 2, then 4, then 8, then 16. In round trip time 5, we assume that an event occurred. The event can be a timeout or 3 duplicate acknowledgements. We don't care because they are treated in the same way. So once this happens, congestion window will be reset to 1, and SS threshold will be adjusted to congestion window over 2. Okay, so congestion window was 16, congestion window over 2 is 8, so now the new SS threshold is 8. And we go back into the slow start phase, so we increase exponentially. Congestion window is 1, next round trip time it becomes 2, then 4, then 8. Once it is 8, the congestion window is now equal to SS threshold, and now it goes into the congestion avoidance phase, where the size of the congestion window increases linearly. And so 8 becomes 9, 9 becomes 10. We are assuming that at this round trip time, another event actually occurs. The congestion window is reset to 1, and SS threshold is equal to congestion window over 2. And it then goes to increasing exponentially because it goes to the slow start phase. This is how TCP Tahoe works. It is simple, it is straightforward, and it acts in a conservative way. The goal of TCP Tahoe is to reduce packet loss without much concern to delay. Obviously, this will end up actually having significant delay because you are throttling back the sending rate. You are decreasing the sending rate every time something happens. The adjustment or the upgrade over that is a protocol called TCP Reno. TCP Reno is very similar to TCP Tahoe except for one thing: the way it treats 3 duplicate acknowledgements and timeouts. So with TCP Reno, you still actually start with slow start. You start with congestion window is equal to 1. SS threshold is equal to 64K. You increase exponentially. If it hits SS threshold, you go into congestion avoidance and increase linearly. The difference is the timeout event is treated differently from the 3 duplicate acknowledgement event. The timeout event is treated in the same way as TCP Tahoe, means that if a timeout occurs, the congestion window will be reset to 1, SS threshold will be reset to congestion window over 2, and you go to the slow start phase until you hit SS threshold, and then you go to congestion avoidance. However, the 3 duplicate acknowledgement event is treated in a different way. The 3 duplicate acknowledgement event is actually treated as a less drastic event. This is because if you receive 3 duplicate acknowledgements, you know that something was lost. However, you know that the network is continuing to deliver packets. That means this packet loss event is probably just a single glitch in the network. Once a timeout occurs, it is an indication that the network was not able to recover from an error, which is more drastic. And so, with TCP Reno, 3 duplicate acknowledgements is treated as a less severe event. If the sender receives 3 duplicate acknowledgements, it will reset congestion window not to 1, but to congestion window over 2, and SS threshold will be equal to congestion window over 2. And it will go into something called the fast recovery state. In the fast recovery state, the congestion window size is increased linearly and not exponentially. Now, the sender will stay in the fast recovery state until one of two things happen. Either the packet that was lost, because we received 3 duplicate acknowledgements, right? So that means there is a packet that was lost, and after receiving 3 duplicate acknowledgements, the sender will retransmit the packet directly. Either the sender will recover from this packet loss, meaning that the acknowledgement for the lost packet will be received, in which case the sender will not actually change anything. It will remain in congestion avoidance and will increase linearly. Or the lost packet will not actually be recovered, and eventually a timeout for this packet will occur, in which case congestion window will be reset to 1, SS threshold will be congestion window over 2, and the sender goes to the slow start phase. Okay? This is actually TCP Reno. Everything is the same as Tahoe, except for the fast recovery state, which is when the sender goes to treat 3 duplicate acknowledgements, and here the congestion window is reset only to congestion window over 2. SS threshold is equal to congestion window over 2. We can see an example just to see the difference between the two protocols. Let us say here, these are the round trip times, the transmission rounds, and the y-axis is the congestion window size. So we start with congestion window is 1, then it increases to 2, then 4, then 8. Once congestion window is equal to 8, we hit SS threshold. Now we go from exponential increase to linear increase. And so 8 congestion window is 8 becomes 9, 9 becomes 10, 11, and 12. Let us say that at round trip time 8, an event occurs. With TCP Tahoe, which is the blue line, it makes no difference what this event is. Timeout or 3 duplicate acknowledgements actually doesn't matter. and so congestion window is reset to 1. Okay, SS threshold is equal to congestion window over 2, and so congestion window was 12. Now SS threshold is equal to 6. Okay, and now TCP Tahoe goes into congestion, it goes into slow start or exponential increase, and so 1 becomes 2, 2 becomes 4, 4 becomes, doesn't become 8. Once it actually hits 6, it has to go into congestion avoidance because now it's equal to SS threshold, and now it goes to congestion avoidance and increases linearly from 6 to 7 to 8 to 9. TCP Reno, which is the black line, does something different. Once the event occurs in round trip time 8, it goes into the fast recovery state. This is actually an indication that the event was a 3-duplicate acknowledgement, not timeout, because it was treated differently in TCP Reno. And so here, congestion window was actually only decreased to a congestion window over 2, so 12 becomes 6, and it goes into congestion avoidance where it increases linearly and waits for this loss event to recover. Obviously here, because we see that the TCP Reno never actually went back to congestion window is equal to 1. And so it's an indication that TCP Reno has recovered from this loss event, meaning that an acknowledgement for the lost packet eventually was received. Makes no difference for TCP Reno to actually stay in the congestion avoidance phase. This is actually the difference between the two. This is an indication that the loss event was 3 duplicate acknowledgements because it was treated differently between TCP Reno and TCP Tahoe. Let us now take an example to see how congestion avoidance and flow control operate simultaneously in the same system. So the example says, consider a host sending data over a TCP connection. The receiver is capable of processing frames at a speed of 5 MSS per round trip time, and the maximum capacity of the receive buffer is 10 MSS. Assume that initially congestion window is 1 MSS and SS threshold is 30. Assuming a timeout occurs in the 7th slot, its effect is observed in the 7th slot, and 3 duplicate acknowledgements are observed in the 10th and 17th slots, and the TCP Reno is used, fill in the following table. So the information says that the buffer space that's for the receive window is initially 10, okay? And the receiver is capable of processing 5 MSS per RTT. That's actually the processing speed of the application. This is the speed at which the application reads data from the receive buffer. And we start for the congestion window with congestion window is 1 and SS threshold is 30 MSS. And there are 3 events that we have to take care of. So this is the table that we start with. In the first round trip time, congestion window is 1, receive window is 10, sending rate is 1. Congestion window is 1, this is actually what we start with. Receive window is 10 because we start with an empty buffer space at the receiver. And so if the buffer space is actually 10, then the empty buffer space or the receive window will be also 10. The sending rate is the minimum of the two. So you look at congestion window and receive window, the sending rate is always the minimum of the two. And so the sending rate here is 1. Meaning that in the first round trip time, the sender will send only 1 MSS. If the acknowledgement for this single MSS is received, congestion window in the second round trip time becomes 2. Receive window is still equal to 10. Sending rate is 2, which is the minimum of the two. Since we are still in a slow start, the congestion window is increased exponentially, so 2 becomes 4. Receive window is 10. Sending rate is now 4. In the fourth round trip time, 4 becomes 8. Congestion window is now 8. Receive window is 10 and sending rate is 8. In the fifth round trip time, congestion window is again doubled, so 8 becomes 16. But now look at what happened in the receive window. In round trip time 4, we sent 8 MSS. Now, the question tells me that the receiver is capable of processing frames at a speed of 5 MSS per round trip time. That means every round trip time, the receiver is capable of processing 5 MSS. In the first 3 round trip times, I was sending 1, 2, or 4 MSS. But the receiver is capable of processing 5. So whatever the receiver receives, it processes it within the same round trip time. This is why the value of the receive window doesn't change. It remains empty because nothing is left at the receiver. The receiver is actually processing everything that it receives. But once the sending rate becomes 8, what happens? The receiver is capable of only processing 5. It receives 8, it processes only 5. And so 8 minus 5, which is equal to 3. This will actually be the number of segments that will be left in the receive buffer. These are the ones that were not processed in round trip time 4. And so if in round trip time 4 we start with the receive window is 10, I send 8 frames, 5 of them are processed, 3 of them remain. So 3 of them will be consumed or will take a place in the receive buffer, reducing the size of the receive buffer from 10 to 7. Okay, this is actually what happened here. So the congestion window is now 16, the receive window is 7, the sending rate is now the minimum of the two, which is 7. Note that here the sending rate is now determined according to the receive window and not the congestion window. The congestion window process is still running independently, meaning that the size of the congestion window will only be adjusted if a timeout or a free duplicate acknowledgement event happens. This didn't happen. The only problem here is that now the receive buffer is starting to become a little bit full. And so according to the size of the receive window, the sending rate is now adjusted. Okay, now if you look at round trip time 6, we see that we did not actually double the size of the congestion window from 16 to 32. We actually increased it only from 16 to 23. We are actually still in the slow start phase, and we could have doubled the size of the congestion window. But what is the rule actually for increasing the congestion window? We increase it by 1 in slow start. We increase it by 1 for every acknowledgement that we receive. Okay. So if we send 2 segments and we receive 2 acknowledgements, we increase the congestion window by 2. If we send 4 segments and receive 4 acknowledgements, we send it by 4. We increase it by 4. Okay. Here in round trip time 5, the congestion window size was 16. That means you could have sent 16 segments or 16 MSS. However, because of the size of the receive window, we sent only 7. So the maximum number of acknowledgements that we could have received is 7. So if we receive 7 acknowledgements, the congestion window will be increased from 16 to 16 plus 7, which is 23. Okay. That's why it wasn't increased to 32, because we didn't actually send 16 segments, we sent only 7. And so we increase it to 23. We are still actually in the slow start phase. That means if you send 23 segments, you can actually send them. And if you receive 23 acknowledgements, you can actually increase the window size to 46. Now let us see what happens. I send in round trip time 5, I send 7 MSS. Okay. Again, the processing speed of the receiver is fixed. It is only 5. So I send 7, I process 5. What remains is 2. So an additional 2 frames or 2 segments will remain in the buffer. So the buffer space was 5. 2 more frames take space, 2 more segments take space. So 7 becomes 5. And so the sending rate is the minimum of 23 and 5, which is 5. Now the question says that a timeout occurs in the 7th slot and its effect is observed in the 7th slot. What does it mean its effect is observed in the 7th slot? That means we actually have to adjust the congestion window size to 1 because it's a timeout. And SS threshold will be adjusted to congestion window over 2. So congestion window was 23 over 2, and we take the floor, then it is 11. So now SS threshold is 11. Now, if I send 5 frames in RTT6, I can process 5. So all the 5 are actually processed. No additional spaces will be occupied in the receive buffer, and so the receive window remains at 5. Now the congestion window in round trip time 7, congestion window is 1, receive window is 5, and so the sending rate is again now 1. And we are in the slow start phase. In round trip time 8, I send 2 segments. And now look at the receive window. I sent in round trip time 7, I sent only 1 segment. I can process 5. And so I can definitely process the 1 segment. But I had 5 segments remaining in the buffer. I didn't process them yet. So I can process 1 that was sent plus an additional 4 from the ones that were remaining in the buffer. And so 4 spaces will now become available, increasing the size of the receive window to 9. Okay? This is actually why. Because in round trip time 7, I restricted my sending rate to 1, okay, because of the congestion window. And so I sent 1, but the receiver is capable of processing 5. So it processes this 1 in additional to 4 more of the ones that were in the buffer, increasing the size of the receive window to 5 plus 4, which is 9. Now the sending rate in round trip time 8 is the minimum of 2 and 9, which is 2. Okay, so in round trip time 9, congestion window is doubled from 2 becomes 4. And now to see what the size of the receive window would be, I sent 2 frames. I can process 5, so definitely I will process these 2, and I can process an additional 3. However, only 1 remains in the buffer in round trip time 8. The maximum buffer size is 10. You have to remember that. So 10 and the remaining space is 9, so there is 1 only available in the buffer, which will be processed alongside the 2 that were sent in round trip 8, increasing the size of the receive window to 10, meaning that the entire receive buffer is free. In round trip time 9, sending rate is 4, the minimum of 4 and 10. Now the question is telling me that 3 duplicate acknowledgements are observed in the 10th and 17th slot. Okay, so in the 10th slot, I have 3 duplicate acknowledgements, and this is treated as a less severe event, meaning that congestion window will be decreased to congestion window over 2. So 4 becomes 2, and SS threshold is equal to SS threshold is equal to congestion window over 2. So 4 over 2 is equal to 2. I sent in round trip time 9, I sent 4 MSS and I can process 5, so there is no change to the size of the receive window. Since this is a 3 duplicate acknowledgement event, I go to the fast recovery state, and in there is congestion avoidance, so I increase the size of the congestion window linearly. Okay, I keep increasing it linearly. Okay. Here, the sending rate is the minimum of congestion window and receive window. So it's 3, 4, and 5. Once the sending rate becomes 6, in the next round trip time, I can process only 5. So 6 minus 5 is equal to 1. And so 1 space will be consumed from the buffer. If it is 7, 2 additional spaces will be consumed from the buffer. So 9 becomes 7. And at every time, the sending rate is the minimum of congestion window and receive window. In the 17th round trip time, another duplicate acknowledgement event occurs. Congestion window will be congestion window over 2. SS threshold is equal to congestion window over 2. And accordingly, these two values are adjusted. The receive window here, in the round trip time 16, I send 7. I can process 5. So 2 additional ones remain in the buffer. So 7 becomes 5. And I increase the size of the congestion window linearly. You can see here that adjusting the SS threshold induces a cap as to when you should switch from slow start to congestion avoidance, and accordingly reduce the rate at which you are increasing the congestion window. Okay. I added here a second example just to show you actually the interaction between everything, between the sequence numbers, acknowledgement numbers, receive window, and congestion. No, there is no congestion window here. You can actually take a look at it and see how the sliding window process operates to increase and decrease depending on how much you are sending. TCP Reno and Tahoe are more or less classical congestion avoidance mechanisms. TCP Tahoe, as we said, it focuses on packet loss. TCP Reno also focuses on packet loss, but it tries to increase or it tries to reduce the delay a little bit. Neither of them have actually any significant attention to delay. Their delay is large because they are conservative in the way they increase the congestion window. Over the years, there has been other congestion avoidance mechanisms that pay attention more to delay. For example, there's something called TCP Vegas that emphasizes delay by adjusting the congestion window based on measuring round trip time. Basically, it probes the network to measure the round trip time. We mentioned before that round trip time is a dynamic quantity because it changes according to the queuing delay in the routers between a client and the server. And so TCP Vegas continuously monitors this value in order to adjust it to a realistic number, and so it can detect congestion before it occurs. If it sees that the round trip time is increasing significantly, this is an indication that the routers are actually suffering, and so it can decrease its rate. There is also another one that is called cubic, and this is the one that is implemented in the Linux operating system. It is called cubic because the congestion window increases by a cubic graph. There is a conservative phase, which is this a slow start phase, and once an event happens, there is a phase where the congestion window doesn't increase at a very high rate. Once this phase starts, there is another exponential increase phase to have the window increase to at a fast speed. And so the idea with cubic is to allow for fast ramp of the window after congestion, followed by plateau where the network is allowed to stabilize, then rapid growth. And the objective here is to allow the congestion window to grow to the maximum capacity of the channel as quick as possible. The one that is by the default in Windows is called compound TCP. It's actually a combination of Reno and Vegas. It has two congestion windows. One of them is handled similar to Reno, and one of them is handled based on estimates of the delay. And the goal of the compound TCP is to keep the average of the two windows constant. So there is one window that focuses more on packet loss, another window that focuses more on delay, and the idea is to keep both at actually a relative constant. There is also another one that is called elastic TCP that was proposed in 2019. And the idea is that from its name, it is a flexible one. It has several metrics that can be adjusted, and it was proposed to increase the bandwidth utilization of different types of networks, such as cloud computing, big data transfer, IoT. So the objective here is to reduce the time needed for the devices to reach a maximum bandwidth, but actually it has several parameters that can be adjusted based on your network needs. Last thing we will discuss is actually connection management, how to establish a connection and how to terminate a connection. We said that to establish a connection, a client has to actually send to the server a connection request and receive a connection response. The connection request is actually called an SYN packet. And if we remember from the TCP header, there was three flags, the R, S, and F flag. S flag is short for SYN. This is set to 1 if the packet is a connection establishment or a connection request packet. Okay. So we already know these two packets, the SYN and the SYN acknowledgement. There is actually a third packet that is called the acknowledgement packet. Okay. And this concludes the three-way handshake in TCP. So in reality, connection establishment in TCP is a three-way handshake and not a two-way handshake. Why did we just actually say it's a TCP connection request and response? Because with the third part of the handshake, with the third packet, you are allowed to send data. That means if you have an HTTP request, you can add it to the third packet. In the first two packets, in the SYN and the SYN acknowledgements, you are not actually allowed to have data. That means these are just for connection established. In the third packet, you are actually allowed to send data. So it's a three-way handshake, but the third packet allows you to send data along with it. Okay. So what happens when the devices send an SYN and receive an SYN acknowledgement? They are actually agreeing on first the initial sequence numbers. In the SYN, the client sends its own initial sequence number, and in the SYN acknowledgement, the server sends its own sequence numbers, and they allocate buffer spaces. The receive buffer, for example, that is used for flow control. This is something that will be allocated in the connection establishment, and the initial size of the receive window will be sent also in the SYN and SYN acknowledgement packets. To terminate the connection, it's actually a four-way handshake. So if you take a look back to the TCP header, there will be an F flag. The F flag is for terminating the connection. So if the client sends a packet with the F flag set to 1, this is a FIN packet. Once the client sends a FIN packet, it closes the socket from its end. Okay. The server will then reply with an acknowledgement and then will send its own FIN packet indicating that the socket is closed. Okay. Now, when the client receives the FIN packet from the server, it will start a timer and send the acknowledgement. If the timer expires before any acknowledgement, before any more FIN packets are received from the server, then it will actually indicate that the that the acknowledgement has been delivered to the server and will terminate the connection completely. Okay. However, during this time, if it receives more FIN packets from the server, it means that the acknowledgement from the client to the server was lost, and it will resend the acknowledgement again. So it's a four-way handshake in order to close the connection, just so that the socket is closed from both ends, from the server end and from the client end as well. That's it for the transport layer, and that's it for TCP. Next lecture, we will go into the network layer. Talk to you next time.